and it can accelerate a 2-ton car to 60 miles per hour in just 2 seconds. The RPM is so extreme that the centrifugal force alone wants to expand the rotor. Think you've seen every twist in electric cars? Think again. Elon Musk just unveiled a motor that doesn't join the race. It ends it. It ends it. No gears grinding, no lag, no ceiling on speed or range. Just smooth, silent power that feels more like science fiction than reality. It's ferocious, it's flawless, and it could bury the competition once and for all. Curious how he pulled it off and what it means for the future of driving. Strap in. The ride starts now. The motor that changed everything. Tesla has just flipped the script on electric motors. For years, they've led the EV race, but this time they've done something far more disruptive. Instead of tweaking an existing design, they've unveiled a motor so advanced it might make everything else obsolete. And yes, it can accelerate a 2-ton car to 60 miles per hour in just 2 seconds. We first got a glimpse of this motor at the Model S Plaid delivery event on the 10th of June 2021 when Elon Musk casually revealed a drive unit so compact that one person could lift it yet powerful enough to launch a full-size sedan into supercar territory. At its core is a rotor wrapped tightly in carbon fiber. At first, that might not sound exciting, but the effect is massive. There has never been an electric motor like this. In traditional motors, metal components swell under heat, wear down under pressure, and eventually fail. That's why they're kept in speed and longevity. Tesla solved this by developing an in-test house process that wraps carbon fiber around a copper rotor at extremely high tension. This outer sleeve locks everything in place, keeps the rotor permanently compressed, and maintains a micro-thin air gap between the rotor and stator, dramatically improving efficiency and magnetic force. Thanks to this breakthrough, the rotor stays stable at extreme speeds over 20,000 revolutions per minute, far beyond the 16,000 revolutions per minute limit where most high-performance motors give out. Motor Trend verified these speeds during testing, confirming that Tesla's new design runs nearly 25% faster than its predecessor, an unheard-of leap in electric motor engineering. The result is a motor that delivers more torque, stays cooler, weighs less, and withstands greater stress without wasting energy. This isn't just an upgrade, and G&D Netricrate. It's a complete reimagining of how EV motors should be built. And Tesla didn't stop at performance. They nailed production too. Each Model S Plaid carries 3 of these motors, producing a combined 1,020 horsepower and 1,050 lb-ft of torque. Yet, each motor is small enough for a single engineer to lift during assembly. Even more impressive, during its March 2023 Investor Day, Tesla revealed that the next generation of these drive units will use 0 rare earth elements, require 75% less silicon carbide, and cost around $1,000 to manufacture. An industry and the performance is nothing short of staggering. 0 to 60 in under 2 seconds. Yes, under 2 seconds. That makes it quicker off the line than almost any car in history, including Bugattis and Lamborghinis. Independent testing clocked the Model S Plaid at 1.98 seconds from 0 to 60 miles per hour and just 9.25 seconds in the 1/4 mile. Top speed, a blistering 200 miles per hour once software limits were lifted. But here's the kicker. It's not just fast, it's efficient. Older performance EVs burn through batteries like rocket fuel. This one doesn't. It channels power into motion with almost no loss. No oversized radiators or complex cooling systems, just clean, stable output. EPA data backs it up. On 21-inch wheels, the Model S Plaid is rated for 348 miles of range and a combined 101 meter PG, about 334 watt-hours per mile. Phenomenal for a car with over 1,000 horsepower. Even real world tests hold up. Inside EVs ran a highway range test at 70 miles per hour, and the Plaid still managed 300 miles on a single charge. That proves this motor can deliver raw speed and long-range endurance in the same package. It solves one of the biggest headaches in EVs is the trade-off between power and range. Normally, the harder you drive, the faster your battery dies, but this motor changes that equation. Now you get both brutal speed and smart efficiency. Tesla is giving you both and delivering it at scale. Thanks to the new design, simplified engineering, and lower material needs, the cost to build each unit has dropped significantly. Whether Tesla passes those savings to customers or keeps the margin, the advantage is theirs. When you push this far ahead, rivals don't just fall behind, they fall apart. Let's see how the competition handled the hit, knocking out the competition. Tesla's competition is falling behind and fast. Not long ago, the EV race looked tight. Big name automakers like Ford, GM, Toyota, and Volkswagen were pouring in billions. Startups like Lucid and Rivian promised bold innovation. Chinese giant buy dominated sales. For a while, it seemed like Tesla's lead might not last. Then came the carbon wrap motor, and everything changed. Legacy automakers still build EVs on platforms originally designed for gasoline engines. That makes their EVs heavier, less efficient, and more expensive to produce. Their factories were built for gas-powered cars, not EVs, and they rely heavily on suppliers for batteries and key parts. Tesla doesn't. Every Tesla is designed from the ground up to be electric. Their factories are optimized for EVs. They build their own batteries, and now they build motors no one else can match. While other companies are still catching up to Tesla's last breakthrough, Tesla has already moved on to what's next. Ford has pledged around $50 billion for EV development through 2026, but its marquee SUV still weighs over 300 more than Tesla's Model Y, and Ford lost over $1.3 billion in its EV division last quarter. Now, GM pledged $35 billion toward EVs by 2025, but its Ultium rollout has been slow, plagued with software and assembly problems. Toyota committed $38 billion to EVs, but is now shifting back to hybrids after weak demand. Volkswagen software division Cariad has lost billions since 2022, leading to layoffs and delays. Startups aren't doing much better. Lucid builds a fast EV sedan, but at $150,000 and only 9,000 cars in 2024, it's struggling despite heavy Saudi investment. Rivian has a loyal following but loses tens of thousands per vehicle and expects more losses ahead. Even Bide, which sold 4.2 million plug-in vehicles in 2024, mostly sells low-cost hybrids and compact EVs priced under $25,000. Outside China, it faces tariffs and trade barriers. Meanwhile, Tesla keeps pulling further ahead. The second big thing was regenerative braking. Normally, when you brake in a car, energy is wasted as heat, but in Tesla's Roadster, when you braked, the motor started working in reverse, converting rotational energy into electricity and sending it back to the battery. This slightly increased the battery's charge and extended the car's range. This was absolutely new and revolutionary at the time. While the AIK induction motor was a cornerstone of Tesla's early innovation, providing a level of performance and reliability that stunned the automotive world, it was not without its own set of intricate engineering challenges. To understand Tesla's true genius, one must look not just at the motor strengths, but at the profound limitations they had to overcome. The core of the issue lay in the relationship between speed, power, and a fundamental physical property known as back electromotive force, or back MF. At low speeds, the induction motor was a powerhouse. It delivered immense torque almost instantaneously, which is why even early Tesla Roadsters could outperform high-performance gasoline cars off the line. However, as the motor's rotational velocity increased, this back EMF, a voltage generated by the spinning rotor that inherently opposes the current that created it, became a significant factor. Think of it as the motor building up its own internal electrical resistance the faster it spun. To maintain a consistent level of power output at these elevated speeds, the motor's inverter had to push against this growing resistance by supplying a significantly increased amount of electrical current. This is where the first major problem emerged: thermal management. The laws of physics are unforgiving. Whenever you force a large amount of current through a conductor, you generate heat, and the relationship is squared. Double the current and you quadruple the heat generated. Those I²R losses. This meant that during sustained high-speed travel, such as on a German autobahn or a long American highway, the motor would produce a tremendous amount of waste heat. This heat wasn't just an inefficiency, it was a direct threat to the motor's integrity. The delicate enamel coating on the copper windings could begin to degrade, potentially leading to short circuits and motor failure. Consequently, a robust and often heavy cooling system became an absolute necessity. This system, typically a liquid cooling loop with a radiator, added complexity, weight, and consumed its own share of energy, creating a parasitic drain on the vehicle's overall efficiency. Simultaneously, the second and more palpable problem for the driver manifested: range anxiety. The demand for immense current at high speeds had a direct and voracious appetite for the energy stored in the battery pack. Draining hundreds of amps to maintain 80 or 90 miles per hour would deplete the battery at an alarming rate. This created a direct and frustrating trade-off for the driver. The desire to use the car's performance capability came at the steep price of drastically reduced operational range. You could have high speed or you could have long range, but it was exceptionally difficult to have both in a sustained manner. Tesla's engineers understood this intricate dance of physics and practicality from the very beginning. They weren't just building a motor, they were designing an entire ecosystem around it. Their brilliance was reflected in the sophisticated software algorithms that managed power delivery, the compact yet powerful cooling solutions they engineered, and the strategic placement of the motor within the vehicle for optimal thermal dissipation. They acknowledged these limitations not as dead ends but as complex puzzles to be solved, setting the stage for the continuous evolution